yesterday so that you remember, and also I clarify certain things, which perhaps I haven't said yesterday. So let me start by telling you about the phenomenology of glassy systems. So, well, you heard about those from Mathieu, but imagine that you have an atomic system that you prepare at very high temperature, then you cool it down. If you cool it down to a temperature which is above the glass transition, not that much above, so this is what I mean by this symbol here, and you measure correlation functions, the relevant ones for your kind of material, what you will see is that the system is able to equilibrate with the environment. It does in a way such that the correlation function decays in a stationary way, as we were saying, it's a property of equilibrium. The integrated linear response also depends on time differences only, so it's also stationary. But what happens is that if you cool down to temperatures which are closer and closer to Tg, the relaxation time, so the time difference needed for the correlation function to decay to some value, say whatever, C over E, where C is the correlation at equal times. Let's call it C bar, the correlation at equal times. So you define a reference value of correlation, and you see that the time difference needed to decay to that value of the correlation increases with the distance from the glassy temperature. So increases in such a way that it seems to diverge. Okay, then, you know, fits become very tricky and complicated and so on, but for sure, what happens is that it increases enormously when you approach a given value of the temperature that we associate with the glass transition. I'm not going to discuss dynamic glass transitions versus static glass transitions. For those who know, let me be a little bit sloppy here because there is no enough time to get into those details. So this relaxation time is called the alpha relaxation time, and it's the same that you will measure from correlation functions or from linear response functions. So for example, this line here corresponds to measuring at a temperature T1, and the other yellow line which accompanies it is also measured at T1. This is measured at T2. This one is measured at T2. This at T3, and the other one at T3. This is what I'm telling you here. And these T1, T2, and T3 are ordered in this way so that here I'm getting closer to this value Tg, and the relaxation is becoming slower and slower and slower. So these curves, it turned out that they go towards a plateau. Of course, in simulations, the plateau maybe is not as flat as I'm sketching here, but in models it is. And this plateau is always the same. So it doesn't depend on temperature. It's the same at the same altitude. And let's call it QG. So it's the plateau where the things will converge to if I were to look at super long, so super low temperatures, getting very, very, very close to Tg. If I were able to equilibrate at those low temperatures, very close to Tg, okay? So this QG is often interpreted as another parameter. And you see, it's another parameter that it takes a non-zero value at the transition. So if I associate this Tg to a transition, and if I associate this Qg to a transition, the value of Qg at the transition is finite, is non-zero. So this is similar to what happens in first-order phase transitions. And other aspects of what's going on in this transition are such that it's not really a first-order phase transition of the ones that you're used to in usual thermodynamics and statistical physics and so on, because there are no thermodynamic latent heat, and it doesn't have the other properties of first-order phase transitions. So this is why this is called a random first-order phase transitions. It has aspects of a first-order phase transition with this value being finite here, and it has other aspects of second-order phase transitions. So the picture that goes behind this description, the analytic picture or the phenomenological picture that goes behind what I'm telling you here, is what is called the random first-order phase transition scenario for glassiness. I'm plotting here correlations and the corresponding linear response. Now, if I do this parametric construction where I plot C here, and this is the C value at equal times, and I plot the associated linear response over there, all these curves are in equilibrium. So all these curves will give you straight lines with the slope given by -1 over the temperature at which you are working. So this T1 is higher, so the slope is smaller, and this T3 is lower, so this slope is higher. So this would be the one for T1, this would be the one for T3, and so on and so forth. So as temperature decreases, these curves become more vertical in a sense. But they are all straight lines with no other features in it. Okay? Now then, what happens if you do the quench to a temperature which is below Tg? If you quench below Tg, the system is no longer able to equilibrate with the environment. It evolves out of equilibrium. And what you observe for the correlation functions and linear response functions at fixed temperature T below Tg, but now you take care of the fact that the dynamics is no longer stationary. There's no longer stationarity. So then you have to take care of these times, the times at which you start measuring. You cannot just simply neglect them and say that the correlations will be functions of T minus T prime and the linear response as well. So what you do in these plots is you fix temperature below Tg, and you measure at different reference times, T prime 1, T prime 2, and so on. So this curve would be for T prime 1, this for T prime 2, this for T prime 3, and the corresponding linear responses as well. So you have lost stationarity, and you see that the relaxation time that you can also measure in the same way, like C over E, it increases with T prime. So the longer you wait until you start measuring, the slower the relaxation of your system, because the correlation needs more time delay to reach the same level.
And now if I approach the the Tg, do you observe the same trend with the curves shifting to the same trend that I have here? Do you observe there when I approach?
But the problem is that if you get close to Tg from below, you will not be able to equilibrate because your equilibration time has diverged. So you will not be able to reach a stationary regime. So you always have to take care of the T prime. So if you wish, this relaxation time here depends on T prime. It also depends on temperature. But temperature I have kept fixed here. So this is fixed, some value below Tg. And I look at what happens in terms of the time now. So the form of the curves is very similar. It's very similar, but there is this, you have to take care of the reference time at which you start measuring. Yes?
Thank you, Professor. Actually, when I looked at it since some time already, I seem to misunderstanding maybe, but at the time constant, at the level of the time constant, I know the delay you talked about is a constant delay.
It's not constant.
Okay.
No. It's something that you vary. So you have time axis. This is the moment at which you quench. Okay. This is a T prime that you choose.
Yes.
And then you measure as a function of T minus T prime. So in an example, you do a simulation. So you prepare your sample, you let it evolve. You set T prime to be, if you do Monte Carlo, 10 Monte Carlo steps. If you do molecular dynamics, okay, 10 molecular dynamics units. You choose it. Okay. You take a picture of your sample. Take a picture. So you have a snapshot. You know where are your particles. You have the configuration. And then you let your dynamics evolve. You let the dynamics evolve, and at all these times, you also take pictures, and you compare those pictures to the one that you had here.
Okay.
And like that, you trace one of those curves.
Okay, okay.
And then you repeat for another T prime, which is 100
more
Monte Carlo steps,
okay.
100 MDSs, and so on. And what you will see is that the decay is different.
Okay, okay. It's okay. Thank you.
Yeah. It's okay? Okay, so this is for what concerns the decay of the correlations and the increase of the linear responses. Now, you do this construction of chi against C, and this is interesting because what happens is that if you take T prime sufficiently long, not just after you did the quench, so you have to wait a little bit, there is some transient that you neglect, you go to a T prime, which is sufficiently far away from immediately after doing the quench, and you trace the C of, let's put it like this, C of TT prime, and you put the chi of TT prime. Whatever the T prime that you choose, you will get a curve that looks like this broken straight line. Okay? So what this means, and as before, as I told you yesterday, the T minus T prime is letting you move along this curve. So this is T equals to T prime. This is T very, very far away from T prime when the correlation decays to 0. So if you're able to see it decay to 0, it will go all the way up to 0. So this construction, this parametric construction, becomes independent of T prime for T prime sufficiently long. And let me write it here. In equations, what this means is that if you take the integrated response and you take the limit, mathematical limit, of T prime going to infinity, of course, it's not infinity in practice in simulations, it's very long. If you take T prime very long, and you fix the value of C and T prime, because you see, this is a function of two variables, T and T prime. One is T prime, which I keep, and the T, I write it as a function of C, T, and T prime, comma, if I want to make it T, I can write as a function of C, T, comma, T prime, comma, T prime. Right? I can invert these curves. These curves are monotonic. The monotonic is a function of T minus T prime, each of them. So I can invert and write T as a function of the correlation value and T prime. I plug it in here. And then I have still a function of two variables, of course. If I plug it in, I have C of the correlation, comma, T prime. And then I take this limit. I take the limit of T prime going to infinity, keeping this fixed to some value C. What this construction is telling you is that this limit exists, and it gives you a function of C, which turns out to have this broken line construction, broken line type. You see what I'm telling you? Fine? OK, so this broken line is what is observed in models of glasses, in different kinds of models of glasses, mean field, but also in molecular dynamic simulations of Lennard-Jones mixtures, hard spheres, different kinds of models that have a glassy transition and have a low temperature glassy phase with non-equilibrium relaxations and violations of the fluctuation dissipation. But you see, in a form which is not very complicated. This part is controlled by the temperature of the bath, as I was saying yesterday, and this part is controlled by a self-generated internal temperature in the sample. Yes?
Letícia, yesterday you constructed to us this parametric space, and you started saying that T comes from a bath,
Yes.
which is white noise bath, and the other one is like colored bath.
Exactly.
So, but now, then can I imagine that in those type of models, I have this type of ideas that you have two, I can interpret this curve as having two baths?
I interpret it as having two baths. One is the external bath, which is there. I'm sure it's there. And the other one is self-induced by the dynamics of the system itself. So you have to think that the dynamics arranges in such a way that the structural relaxation occurs as if there was a bath at this external temperature here, but not a stationary bath, because there is this T prime dependence that it's.
But the bath is self-induced by the dynamics itself.
Exactly.
Okay.
Yeah.
Yeah.
That's the picture.
That's an effective stuff.
Yeah, exactly.
Okay.
Yeah. Everybody there?
I have a
Yes,
quick
please.
question. I understand that in the limit of infinite T prime, you get this single curve, right?
Yeah.
That doesn't depend on T prime anymore.
Yeah.
But what happens for lower T prime? Do you have a bunch of curves that you
Exactly.
asymptote to this?
That's right. So for lower T primes, you will get curves that go like this, and progressively.
And they don't have the kink, or do they have the kink?
No, they are here. They are continuous. They don't have the kink, but the kink becomes more and more visible
More
as T prime
pronounced, yes.
increases.
Okay.
Yes. Yeah. So something else that had to be said is a little bit of discussion of these curves. So the Q, which I plot here as this plateau, is no longer the QG. It's a Q that corresponds to the low temperature behavior, and it's something that depends on temperature. It has to do with the size of the cages, if you think in terms of particles in interaction, or when I go back to the problem of coarsening, it has to do with the magnetization of the sample. But the other feature that's here is this T prime dependence, and the fact that the relaxation time becomes longer when T prime increases, because, again, the T primes are ordered in this way. T prime 3 is longer than T prime 2, is longer than T prime 1. So this is what is called the aging effect. And what it's telling you is that when you go to longer reference times here, so say that this is number 1, this is number 2, that's number 3, you have to let your system evolve longer to reach the same level of the correlation. So you have to wait. I mean, not wait is usually the name wait is called is associated to this choice of T prime. So this is called the waiting time, the time you wait until starting measuring. And if you wait longer, you also have to let the system evolve longer to decorrelate by the same amount. So it's like the system became more stiff. More, it doesn't move so much. It moves less and less and less as time goes on. And for that reason, you have to let it evolve longer before it decorrelates by the same amount. So this is the aging effect, and it has been observed in so many different kinds of glasses. And there is even a book of a Dutch researcher from the 70s, actually, who measured, aging in all sort of polymeric glasses, especially, because they were of interest for applications at the time, for uses, industrial uses. So that's the aging. These are the violations of FDT, which are relatively simple. And the other thing I started saying yesterday was about what happens in a problem that we can understand microscopically. Because if you look at your configurations in a glass, you don't see much, right? You see particles, they're more or less disordered. You cannot really understand from a microscopic point of view which are the rearrangements that are leading to these decays and so on and so forth. So everything is a little bit difficult to visualize. But there's other problems where this phenomenology up to a certain point is realized, which are the problems that undergo domain growth or phase separation, which are of a similar kind. So those problems typically have second-order phase transitions. So differently from this random first-order phase transition, if you come from above the critical temperature, you will not see this plateau here. It's like saying that this QG went to 0 at the phase transition coming from above. So there is no finite QG. This is what I wrote here, because the phase transition is second order. You can cook up problems which undergo domain growth and have first order phase transitions, but the more usual ones don't. But now if you quench below TG, then what happens is that you have something exactly like this, only that the linear response is much weaker. So what we will have is something like this, but then the second curves, the second and the third will be lower and lower and lower until eventually they will disappear. So in the domain growth problem, you will eventually get something like that for a sufficiently long T prime, and not the second part of the increase of the linear response. But the correlation is very similar to what I wrote there. This is a difference between problems which undergo domain growth and problems which are of glassy nature. But now let me tell you a little bit more about, again, with drawings first and with some calculations later, something about domain growth that lets you understand, what is the origin of this first decay here and this second decay over there in the situation in which you can understand it, from the microscopics. So domain growth and dynamic scaling, I will introduce. So imagine that you have the easing problem. That I introduced yesterday, or the equivalent time-dependent Ginzburg-Landau description where you represent your configuration with a scalar field that is just a coarse graining of the spins over some little volume of box of some size V. Just to say, OK, there is a way to write a Langevin equation for this. This is a Langevin equation of the ones we have been discussing. And it's an overdamped one. And what you can propose, a la Ginzburg-Landau, I hope you know about Ginzburg-Landau, is some force, let me call it F, of phi, that in the Langevin equation will favor configurations of uniform phi that correspond to the magnetization up or magnetization down. So basically, this force derives from a two-well potential with two minima at minus phi naught, plus phi naught. And these are magnetization up, magnetization down. So you can do it both in Monte Carlo dynamics for easing or overdamped Langevin for Ginzburg-Landau. So if you look at what happens, this I said it a little bit yesterday, but let me represent it again here. Imagine that I have a system in d dimensions, but I focus on one direction. This is one direction, one spatial direction. So let me plot phi at a given time as a function of x, so along one direction, in different situations. So if I plot it in equilibrium at low temperatures, so say when the spontaneous symmetry breaking has occurred, and imagine that this is the state that has been chosen by the spontaneous symmetry breaking, so I'm at positive magnetization, let's say. At a given time, I will get something like this. The average of this line is phi naught, but there are some fluctuations because I'm at temperature below Tc, and this temperature is larger than 0. If temperature were 0, it would be flat. But since there is some temperature, I have fluctuations here, a little bit like the particle in the harmonic potential that I was telling you about. You know, there will be a little bit of fluctuations, and these are thermal fluctuations. Now, if I take a look at the configuration at another time, I will get another curve like this, but of course the fluctuations will not be at the same places. So it will be a little bit different. The statistics of the fluctuations will be the same because I'm at the same temperature, but you know, apart from those fluctuations, I will be around phi naught as well. So this is in equilibrium. This is equilibrium at this temperature there. Now, what happens if I start from a random initial condition? Random initial condition means that in this little plot here, I'm here. Random initial condition means that phi is 0, because I have as many pluses as minuses, and this averages out to 0. So let's do it in the other plot, in the other panel here. So if I start from a random initial condition, at the initial time, I have a configuration that is something like this. This is T equals 0. Then I quench it to a temperature below Tc. So I quench it to a temperature where the system would like to equilibrate. But as I was saying yesterday, in some places, because the fluctuations are such that they favor the positive phi, a little bit later, it will be like this. Let me make it higher. A little bit later, it will be around phi naught with fluctuations. But then somewhere else, it will be somewhere else. It will be, you know. The configuration will be something like that. So this one is at T1 larger than 0. So there will be domains. These are called domains. Domains of positive magnetization, domains of negative magnetization. They don't all have the same length, but somehow there is an average length that one can see that characterizes the size of those domains at the time at which you took this picture. Is it clear? But you see, there will be as many positive as negative regions in the sample. And if I average out over the whole system size, I will get 0 again, because I have as many positive as negative phi's. So if I come to this plot, the average over the whole system, phi will be at 0. Then if I take, oh, sorry.
So maybe I didn't catch everything, but this is at a constant magnetization. So you have fixed magnetization and temperature, or the external field to 0?
I don't have external field, and I don't have constant magnetization. But the magnetization to come here you will see, I will need a time that diverges with the system size. This is 4 times which are finite with respect to the system size. And I will see these domains start growing and having a typical size, but this typical size is finite at all times that don't scale with system size. Okay? Other questions? So if I repeat these, let me give you a name. So these things are called domain walls. And those are called domains. Okay? You see that the energy of the problem, the excess energy with respect to the one that you would like to have in equilibrium, is localized close to these interfaces, because it's there that you have a big change in the field and you pay a lot of elastic energy. Yeah.
The way you drew it, it looks like each domain is roughly the same size. Is that just to scale or no?
They are not exactly the same size, but there is a typical size.
There's a scale?
There is a scale. Okay. And this is the scale that I'm calling here R of T1. That if I look at the picture a little bit later, what may have happened is that this domain wall is erased, because imagine that these two, somehow, they start moving in opposite directions. That this starts moving like that, and that starts moving like this. And then maybe later, what will happen is that you will have a configuration that looks like this. These domain walls have been erased, and you have a longer region in space which has positive magnetization, and here you have a longer region in space that has negative magnetization, because for some reason these ones start moving like that, and so on and so forth. So in the yellow configuration, I can also visually and also quantitatively observe, measure a length that grows with time. The yellow one is longer than the white one.
Do you ever expect an entire region to sort of stochastically flip, or?
Well, the probability for that is very weak. I mean, it's almost zero. Yeah. So what happens is that the domain walls move. Okay. And you can, this is very old. This is Allen and Kahn. In the 70s, studied the problem for the domain growth in ferromagnetic systems, what is called non-conserved order parameter, non-conserved magnetization, non-conserved order parameter dynamics. And what they showed is that in 2 dimensions, I'm drawing in 1 because it's easier, but in 2 dimensions, say that you have a plot where you have positive magnetization here and negative magnetization there. What they proved is that the walls move in the direction of decreasing the curvature. So you see, so this is Allen Kahn from the 70s. And then you can, from there, estimate what is the functional form of this R of T that I will give you now in a second. OK, so domain growth, because the domains are growing in time. And there is this typical length scale that appears, and that I guess that Jeff will discuss a bit more in detail this afternoon in his lecture, in his talk. But what is it measured from here? Well, you can measure this R of T. And let me give you the expression, and then I'll tell you how you can measure it. One way of estimating it. So for these problems of domain growth, typically R of T grows like a power law with an exponent, which is called a dynamic exponent. The way of writing it is R of T, T to the 1 over T. This is the standard notation. And how can you measure it from a simulation, say? But you measure it taking advantage of what is called dynamic scaling. So it's an assumption. The assumption is that whatever you measure in these problems, which are driven by domains which grow, can be scaled in terms, so can be scaled in such a way that times appear only through this R of T. So what do I mean? Imagine that you want to compute the correlation functions I was talking about before. So you compute this C of R of t and t prime. And you observe that they have these kind of forms, just like that. So you observe that there is a first decay towards a plateau. And this, what does it mean? It means that you have not let a lot of time pass after you took the white picture, let's say. So the world hasn't moved. The only thing that changed were the fluctuations within the domains. So those are like equilibrium fluctuations. It doesn't matter if there is the wall or if there is no wall. It's just the correlation because of thermal fluctuations. So this part here is just, equilibrium like thermal fluctuations driven by the bath. And OK, it's not interesting. But if you look at time delays which are long enough, they're here in this context. You say, let me talk about, or let me use dynamic scaling. What does it mean? It means that the times here cannot appear independently and alone. They will appear only through R of t and R of t prime. And moreover, you say, like in scaling that you do in critical phenomena, you assume that in the non-equilibrium relaxation, where t minus t prime is sufficiently long, otherwise stated, where c is below the plateau, then the c scales as a function of R of t over R of t prime, or R of t prime over R of t, the same. It's an assumption. But you can make it. So you can make this assumption. And OK, so then what you can try to do is to say, well, let me try to see if I have an R that allows me to scale the functions. And you do a scaling plot. You can also do another kind of measurement, which is instead of comparing configurations at different times, you can compare configurations at the same time, but at a given distance. So this little r here is like the distance. Say that you pick a position here, and you pick another position there. They are at a distance r. Of course, you do it in d dimensions, but OK, the drawing is in 1. And you see how the correlation at a given time, so on the white curve or on the yellow curve, depends on the distance and depends on time. And this argument is telling you that if you look at distances where you have domain walls within the distances, not very short distances, because if you look very shortly, you are within the domains. And then you will not capture the presence of the domains walls. So you look at sufficiently long distances, this C of R of t will be another function, let's call it f bar, of R, which is external, but t can only enter through R of t. So it should be a function of little r over R of t, for r longer than, or at least of the order, longer or equal, let's say, than R of t, because otherwise you are within the domains, and then you only see the thermal fluctuations, right? So by doing this kind of scaling plots, you can extract the R of t, and you will get this, and you will estimate the z. In the case of the Ising universality class or the time-dependent Ginzburg-Landau corresponding Langevin equation, you get z equals 2. Let's write it here. And this z equals 2 can also be obtained with the Allen-Kahn argument. In other cases, it's more difficult to do an analytical argument. So for example, if you conserve magnetization and you consider the problem of phase separation, where you cannot kill a particle to create another one, so you cannot kill oil to make water, you just have to exchange. In those cases, z is equal to 3. Remember the 3 I was talking about in the colloquium? So that's this number 3. And if you have randomness, so if you have quench disorder, pinning centers, things like this, well, Ezequiel knows better. And then instead of being a power law, you will have logarithmic laws. So the dynamics becomes slower. The walls can move less because you pin it. You stop it with, I don't know, pinning centers, different kinds of things. So if you have randomness, you get slower growth than with the pure systems, easing or phase separation problems. Now, in this problem, everything is very simple to visualize. You understand that you have these thermal fluctuations that control the approach to the plateau, which is the magnetization squared, which depends on temperature. Perfect. And then you see that these have to do with the motion of the domain walls. In the glassy problem, you cannot identify domain walls or things like this, so you don't really know very well what this structural relaxation corresponds to in terms of microscopy. But it's there. And you can also scale the curves with some R of t, only that you cannot say, what is it R of t? What is it enclosing? This is not clear. But there is a scaling of those curves, which is observed numerically and experimentally as well. So it remains an open issue. Now, how do I see that the relaxation gets slower when time increases? Like these phenomenological plots are telling you, if I have a scaling of this kind. How do I see it mathematically? Is this consistent with that? Okay, let me write it again. So it's very simple. Imagine that you take the derivative of c with respect to time t. So I fix t prime, and I look at how the correlations here change with t. So it's like getting, in one of these curves, and I see how this slope is, well, what is the slope over there? This is what I'm measuring here. So, okay, I take the derivative. I have to do f prime. R of t prime is not touched, but then I have the derivative of R2. I have this. This is time derivative, right? I'm just taking the derivative of what's inside. So I can do this. All this is another function of R of t prime over R of t. And this is the logarithmic, or the derivative of the log, better said, of R of t with respect to time. Now, if R of t is something that grows with time, in particular, if R of t is like t to the 1 over z, well, I take this derivative, so this will be 1 over R of t. Well, I can do it over there. I don't need to go through the log. Just let's do it there. So if R of t is a power, then here I have 1 over z, t to the 1 over z minus 1 over t 1 over z. So the part in 1 over z goes, and I have that this is proportional to 1 over t. So it's decreasing when t increases, actually goes to 0 when t increases. So these curves are such that, if you look at how they change as a function of this direction, their derivative is going to 0. Now, what happens if I take the derivative with respect to t prime, where you do the calculation and you will see that it also goes like 1 over t. So if you do, instead of that, if you do with respect to t prime, well, this part will change, but you will also get a 1 over t. So the dynamics is getting slower and slower as time goes on. And this is captured by this kind of dynamic scaling. Okay? So it's capturing dynamics getting slower.
I think I missed just something. You still had that function of R of t prime over R of t.
But you look at it at R of t prime over R of t fixed.
Okay.
So if you fix R of t prime over R of t, is that you're selecting the c at which you look at it, and at that value, you look at the derivative.
Okay.
So you select this level, for example. You select, should do it with the blue, but I don't know where the blue is. So you select this level here, and at this one is for t prime fixed, you look at this derivative. So it's going, decreasing as I move along this direction. And then I can also do it with respect to t prime. So I compare this one with the next t prime, I do the derivative at t fixed, and then I get that it also goes to 0. So it's getting slower for increasing times. Okay, so what else do I want to say here? Luis was asking yesterday, what happens with the domain growth when I do this kind of construction? I told you that it gets flat, so it will do something like this and then gets flat. So let me get the green, be consistent with my colors. So the domain growth will do this and then gets flat in the limit of t prime going to infinity. And it's something that, okay, it's observed, but we don't fully understand why this is like this, but it's like that. Both in simulations and in some calculations that can be done. Other questions here, because now I'm going to do a calculation, finally. Yes?
So you explained that with aging, the material of the system gets somehow stiffer, no? And then
I don't think it's on.
Yes, it's on.
Okay, sorry.
It gets stiffer, and then things are slower and slower in time. We can also get something like that by annealing, with the temperature ramp or mechanically annealing the system, etc. And the physical picture is completely the same. Would you say that if I anneal my system, then I can use one of these quantities to say what I've done is equivalent to have waited this amount of time, or if there is something physically different in
No, I think it's the same. I think you can do the same kind of scalings. You know, in the Kibble-Zurek scalings have been very, I don't know if you know about that, but it's something that has been super fashionable in other fields, not ours. And for us, it's completely trivial. So basically what they do is they go slowly through the critical point, and then they continue going slowly within the phase, the low temperature phase, let's say. And what they claim, wrongly, is that everything is decided when you go through the critical point, and that nothing happens later on. And this is not true. You may gain some time. You may, because of spending a lot of time close to the critical point, where the dynamics is a bit faster, you gain a little bit. But then you have to do scaling, and you have to consider that things are still, domain walls are still killing themselves, or vortices are still killing themselves. It could be slow. Maybe you don't see it in the experiment because you didn't have time enough to see it, but it's there. I mean, it will happen. Yeah. So it's just that you may have to consider also the time that you spend through the critical point, and but globally it's the same.
Okay, thank you very much, Prof. Actually, it's true that I'm trying to understand that the yellow color, the R out of T2. Mm-hmm. Yes. Actually, the whole structure the fact it goes, and then it goes down, then it goes up. Actually, I've not understood how to get it, and let me say also its impact, its physical meaning, if I can say it that way. If I'm
Well, the way you get it is that I have this double well structure, which is, if you wish, the potential that is controlling your other parameter or your field, which is this phi here. But in some places, the system will choose the positive magnetization just because there were, if you think in terms of spins, imagine that in this place, you had a situation like this. Just because, it turns out that for probabilistic reasons, you have a minus spin surrounded by positive ones. So since there is an elastic cost to have an interface between this spin and this spin, this spin and this, it's better to flip it. So here, the system will flip and will create a domain of a given size of 3 that it has positive magnetization. But then somewhere else, the opposite situation may occur. And then somewhere else, the system will have to reduce its energy to choose this other configuration here. Because when you do this plot, you have to recall that there is an x. So this plot corresponds to the field at each x. So somewhere it chooses this one, somewhere else it chooses that one. But then it's costly for the system to have domain walls. So in the course of time, it wants to erase them. But it takes time to erase them. And this is the process of domain growth.
Okay, thank you very much.
So your question reminds me that I haven't said something very important, which is that if the growth of the domains is like this, if I want to order the system everywhere in the same direction, I will have to have that R of t should be of the order of the system size. This L is the linear system size of my system. So R of t should reach L to have a uniform homogeneous configuration. But if R of t goes like t to the 1, t over the 1 over z, and it has to be like L, this means that time should go like L to the z. So I need a time of the order of L to the z, at least, this is like a lower bound, to equilibrate my sample. And this diverges with system size, because if I take L to infinity, well, this goes to infinity. So to equilibrate one such sample, I need to look at times which scale with system size. If I remain below this time regime, this time scale, I will always have these two kinds of domains, up and down, right? So in simulations, depends on what you want to study. If you want to study the non-equilibrium process, you have to choose a very long system size, very large system size, and you will always be sure of being below this time scale. If you want to study equilibrium properties, you have to study small enough systems so that your simulation or experiment goes beyond this time scale. And you see that here it's very clear that the time scale scales with system size, it scales with the number of spins, if you think in terms of spins, and diverges in the thermodynamic limit. So in the thermodynamic limit of L going to infinity, you're always not reaching this equilibration time. Yes?
Are these values for the Z exponent independent of dimension?
They are independent of dimension, yes. So this is the class which is called non-conserved order parameter dynamics. So it's like for magnetic systems with a scalar order parameter. This is for conserved scalar, non-conserved order parameter, which is a scalar as well. But then you can have other classes, right? If you have conservation laws, and you can have other values. But they are independent of dimension, yes.
As a kind of follow-up, if I have a different protocol, like I start with a small magnetic field, positive, and select one
you select
single,
one.
And then I switch the field to the other sign,
yes.
And then I have domain growth of the other.
Right, but then it's a different process, because you start from another configuration, you've switched the field, you have to turn it around. So it's nucleation phenomenon in that case. So it's a different kind of process. You have to nucleate a face of the other color, and that should, you know, build up and be, the fluctuation should be sufficiently large so that it grows. So it's a nucleation thing, yeah. Yes?
Hi. Yeah, I have a question about the conditions for the relation for the sea. You say that that holds from a non-equilibrium relaxation. Is that the same as being stationary?
No, no, it's the contrary. It's here. It's when you are in these kind of situations where you see you have this T prime explicit dependence of the decay of the correlation functions. And what I said is that it applies to what happens below the plateau.
Okay.
Because above the plateau is just the thermal fluctuations. Below the plateau is the domain wall motion and annihilation.
Okay, thank you.
Yeah. Some other questions? Okay, so now let me do one calculation, or at least sketch a calculation, to tell you that all these things, domain growth and glassiness, can be captured with a family of models which are mean field in nature. So you will see in which sense they are mean field, and for which you can write down this. Well, in the case of domain growth, you can solve them analytically without much effort. In the case of the glassy ones, you can derive this dynamic mean field theory exactly. For them, it's exact. And then you can solve it. Erase everything. Okay, let me stop here. So this is the family of models which are called p-spin models. In the spherical version of them. So imagine that you have a Hamiltonian. Take a Hamiltonian. Let's call it, no, I don't call it. So I have a Hamiltonian where I have interactions among groups of p spins with couplings that I will choose in a second, and that I sum over all possible groups of those p spins. So it's easier to see if p is equal to 2. This is just this familiar model where you have two body interactions with couplings which are Jij and just 2. You know. Now, usually when we work with spins, we have Ising spins, but it's difficult to write equations and solve problems with Ising spins if you do dynamics. So it's simpler to work with the spherical cases. What does a spherical case mean? It means that you add a spherical constraint. A global one. So you see, now the SIs are real variables. They can go from -infinity to infinity, but you constrain them so that the sum of the squares of them is equal to n. If these are Ising spins, this constraint is obviously satisfied, but it can be satisfied in different ways as well. So what this means is that you're working with, you can visualize this as in configuration space, say that n is equal to 3 to make a plot. So in configuration space, these S's are constrained to live on a sphere, and on a sphere of radius square root of 3. Of course, there are the negative values as well, but to make the drawing, I do it this way. And you can think that your configuration is some, some vector S, which has these components. So the vector S has components S1, S2, S3. And it lives on the sphere. Good. So you can impose this constraint, adding a Lagrange multiplier, Z, that multiplies the constraint written this way. Okay, you can write it this way. You plug it in there, and you multiply by Z, and Z is the Lagrange multiplier that imposes that constraint. And of course, you can do it at this level or in the P equals 2 case as well. Now you say, I couple this problem to a bath. And then I write Langevin. And I can write Langevin on the S's very easily because the S's are real variables. If I were to write Langevin for Ising, I would be in trouble, right? So I write Langevin for the S's. Let's say that I set gamma naught to 1 to make notation simpler. And then my equations are just that, okay? So I have a noise, and I have a friction for each variable, and I have a force on each variable that comes from the Hamiltonian, which is over there. Okay. Now, to complete the definition, yes? Yes, yes. So if you wish, let's write it like this. It does include the Lagrange multiplier. Yes. What you will do is that you will write these equations assuming that Z is God-given, and then you will use the constraint that is here to fix the Z. So you write the equations as if C were known, and use the constraint to fix it later. You will see how this goes in a particular case. So it turns out that if you choose these couplings to be random variables, random Gaussian variables with zero mean, and variance scaled with n here, in a convenient way, in a good way, you will have a good thermodynamic limit in the sense of taking n going to infinity and getting non-trivial results. And you will capture, with this first case, when P is, for example, 3, you capture the glassy problem. So you capture the problem with this plateau here below. You capture everything. You capture this, and you capture this dynamic scaling, and you capture everything. So I'm not going to do it because it will be, it would be too long. I don't have the time. But what I want you to know is that if P is equal to 3, you get this random first order transition for glassiness. While if you take P equals to 2, you get domain growth. You can complain and say, where is the space here? I mean, everybody is interacting with everybody else. When I say you get domain growth, I mean that you get the properties of domain growth, like, for example, T star going to infinity, scaling, and some other features of domain growth for p equals to 2. Not for p equals to 3, it's a different class. So with this parameter, actually it's p equals to 3 or larger, any p larger or equal than 3, that you get these other kind of features with this almost first order phase transition, which is not really a first order phase transition. Of course, I mean, no time to do it in detail, but what I want to do in detail a little bit is this case here. Because it's nice and it's simple. So let's do it. How do you solve this problem? So this problem, you can solve it with no need to go to the dynamic mean field theory formalism. Actually, looking at the dynamic mean field theory formalism, you can see a little bit what is the origin of the difference between p equals 2 and p larger than 2, but OK, that's a little bit technical, so I won't tell you how it goes. But how to solve the p equals 2 case? If you have p equals 2, you have here a coupling constants, which, you see, this term is quadratic, right? So you can diagonalize this term if you go to the basis of eigenvectors, of this matrix. So what I mean is that for p equals 2, I have these jij's, which I can consider to be the elements of a symmetric, real, n by n matrix. Let's call it this way.
Letícia, just
yes.
A clarification. So, but you keep p equals to 2, but you keep the constraint on spherical.
I keep the spherical constraint.
So the Hamiltonian has 2 terms. Okay.
Exactly. It has 2 terms. It also has the term that's here. Right. Also that one. So I have the jij's I organize as the elements of this symmetric real matrix. So it has eigenvectors and eigenvalues, which I'm going to call lambda mu, the eigenvalues, and v mu, the eigenvectors. And mu goes from 1 to n. Right? So I can diagonalize both the Hamiltonian without the z and the term with the z by going to the basis of eigenvectors of this matrix. And if I do that, the Hamiltonian becomes, yeah, I forgot a 1/2. We put a 1/2 here. Okay. Let's put the 1/2. And also the 1/2 here, so that I can write things more nicely. So the Hamiltonian becomes this, where I have defined x mu as the projection of the vector S on the eigenvector mu. So that's the definition of x mu. So this became almost independent harmonic oscillators. You see, because I have here the harmonic oscillator term with different spring constants. This is another quadratic term multiplied by z. So if z were external, this would be a quadratic Hamiltonian, but z is not external. Z has to be determined to fix the spherical constraint. So z is a function of the x mu's. And if I do dynamics, z could be a function of x mu's and the velocities, x mu dots. So x mu depends on the configurations of the system. So this is not an ensemble of independent harmonic oscillators. And this is what makes the problem non-trivial. Simple to solve, but not trivial. So not independent oscillators. Now, what you can do is you can write the Langevin equation for this problem in this new basis. So what this new basis means is that I have, in my sphere here, I have rotated the sphere in a sense. I have rotated in some way the axis. So say that this is V1, this is V2, this is V3. And I look at, well, change of variables, right? So I can write the Langevin equation for this. It will be, I put gamma naught equals 1. Which signs did I put? OK, I have to, let's put plus here. It doesn't matter. The z will be, let's put this notation here. Plus noise. So these are the Langevin equations, and I have n Langevin equations, which are, as I said, almost the Langevin equations of the harmonic oscillator that we have already discussed, but for the fact that they have this z here. So the z in dynamics will be a function of time. So let me put it explicitly. And what I can do is I can solve these equations, assuming that I know z, and fixing the z later on. So I can write, as we did in my first lecture, sorry. I'm writing, trying to be fast, and I'm making mistakes. OK, so it's not difficult to see that this is the solution to that linear equation on the axis, assuming that I know z. Fine. So now let's say that I have to impose the spherical constraint to get the z. So how do I impose the spherical constraint? Well, it has to be that at all times, the sum of the x mu's squared is equal to n, because it's like the modulus of the vector. The modulus of the vector is n squared, and it's conserved, or square root of n, the modulus of it. Well, OK, if you put the square. You see what I mean, this. Now, I will impose this on average over the noise. And what you have to do is you have to plug in this solution here, average over the noise. The noise will be cancellations and so on and so forth. In the end, you get an equation for z of t. It's not a very simple equation, but it's not an impossible equation either. So you get a closed equation for z of t, and you solve it. So you get the time dependence of the z of t that then you plug in there, and then you have the full solution of your problem. OK? So this is completely solvable directly from looking at the Langevin equation. Now, why this problem is similar to domain growth? Well, because first of all, you notice that when you look at the equation, there is a critical temperature that depends on who are the lambda mu's that you choose, because I haven't told you who are the lambda mu's. I just told you that the lambda mu's were the eigenvalues of a Gaussian matrix with real elements. if you take n sufficiently large, you know that the eigenvalues of a Gaussian random matrix of this kind are distributed according to Wigner's semicircle law. So there are eigenvalues in a finite interval of lambdas. So actually they are, with some normalization that we conveniently choose, they are distributed between -2 and 2. Let's put an energy scale here because they are like energies. So they are distributed between 2j and -2j and 2j, and j has to do with the variance of the elements. It's the scale of the variance of the elements of the matrix. So it's the scale of the j's, basically. So you know that the eigenvalues are within this interval here for n going to infinity. If n is not infinity, you will have some tails over there. Now, what happens is that this problem has a critical temperature, which is a function of j, which is actually equal to j, where the system dynamics changes from decaying fastly, correlations decay fast to 0, nothing special, to a low temperature dynamics where the correlation functions decay in the form that I just erased over here. They have aging and so on and so forth. Now, why do we say that this is similar to domain growth? Because if I look in configuration space and I try to understand what's going on with the configuration of my spin, with this vector, say that the vector started, let me do it with a different color. Say that the vector started here. When I do the dynamics at low temperatures, below Tc, what the system tries to do is that the spin tries to align in the direction of the maximal eigenvalue. So say that I organize things so that lambda n is here, is the maximal eigenvalue with index mu equals to n. So what the spin is trying to do is trying to order there. And this trying to get the spin vector towards the v of n, one can interpret and one can see that it's the same mechanism as the mechanism of the domain growth, where the field, if I look at it in Fourier space, and if I look at it as a function of momentum, the wave vector, if I look at it as a function of wave vector, what this is trying to do is trying to go to the momentum equals 0, to wave vector equals 0. So the phi, let's say that the phi of k equals 0 is growing, and all the other modes, all the other wave vectors are going down. So k equals 0 in the domain growth, which is the homogeneous solution, order everywhere, is associated to this, going to this direction over there. And this can be made a little bit more precise, but OK, I don't have a lot of time to say. So this is just one example that can be solved fully. But it's a model that belongs to this class that as soon as you put some more nonlinear interactions here, more linear than just what comes from the spherical constraint, changes class is like changing universality class in terms of the dynamics. Now, last thing I want to say is that in the first lecture, I talked a lot about closed open systems. So both this case and this case can be studied in closed conditions. So what does it mean, closed conditions? Instead of working with the Langevin equation, let's work with Newton. Let's say that instead of putting the noise and putting the friction, I switch them off, but I put inertia. So the yellow problem, when p is equal to 2, is a model that has been known for 200 years and is due to Neumann, the one of the boundary conditions. Of course, he was studying this problem for n equals 2, n equals 3, and he noticed that he could solve it. He could solve the dynamics exactly, So the problem was integrable for n equals 2, 3. Later, of course, closer to today, people have studied for finite values of n, and they have extended these exact solutions for n equals 4, 5, I don't know, finite values of n. We are interested in the n going to infinity limit because we want to say things about equilibration or non-equilibration, generalized Gibbs ensembles. Remember what I said in the first lecture. So what we have been doing with Gustavo in Buenos Aires, Nicolás Nessi in La Plata, some students of mine in Paris, and now also with Daniel Stariolo in Rio, and Rafael, who's here, is to study this Neumann problem in different versions of it, and asking different questions. And we have asked questions about, does it equilibrate, under which conditions, to which measure, and so on and so forth. And there we saw appearing the relevance of the generalized Gibbs ensembles instead of the Boltzmann one, because the model is integrable. So it's an integrable problem. And what is nice about it is that it's an integrable problem, but it's non-trivial because it's not just harmonic oscillators because of the spherical constraint, and this Neumann knew already, of course. But it's rich. It's relatively simple to study with techniques from these other systems, the kind of tricks that we know. And we can check many things. So, okay, don't have time to tell you about. You can discuss with Rafael, who has a poster on this and what we are trying to do. And I think that I will stop now. So, thank you. Of course, questions?
Fascinating. I do have a quick question about
yes.
this is a beautiful calculation, and my question is about the literature.
Yes.
Have people explored, for instance, other ensembles
yes.
of random matrices, correlated and things like that?
Correlated, not.
Correlated,
as
not.
far as I know, not. With Daniel Stariolo and his former master student in Rio, and also a student of mine, we looked at finite n corrections. So, what happens when you don't really have n going to infinity, to try to see the approach to equilibrium and the different time scales that have to do with equilibrium and the fluctuations of the eigenvalues there, Tracy Widom, these kind of things. Yeah. So that has been done. But the idea that we have, which I think is, we can argue it in different ways, is that if you have the lambdas, which have a finite width of validity, they don't go to infinity, there's a net here, all the kind of the scalings and so on are controlled by the way this distribution follows to 0 here. And this you can see. And for all of them will be more or less the same, apart from little details. Now, if you have tails, so if you have tails, things are more complicated. In particular, the energy is not bounded from below, and this makes some other features appear. And this we looked with Guillaume Semarjian, my former student, many years ago. But correlated matrices, I don't think that people have looked at. Yeah.
I have a question concerning exactly this, very related to that one, because this is expected to have a random matrix, right?
Yes.
And I was thinking that perhaps when you are in T below to TC, you have correlations, and then this would not be like that. I'm surprised.
This is external. This has to do with the quench disorder that comes from the JIJs. And the JIJs are the parameters that you choose at the beginning.
So this is fixed?
It's fixed, exactly.
Okay, I see. There's another bit. Okay.
Yeah.
I have another question, but I will ask.
More questions?
Yeah, this is a question a bit related to the one that he asked. Has anyone tried another constraints?
It's more difficult. So in the context of the integrable problems, people have used elliptic constraints, for example. And they're all Neumann models of different kinds, where you're not on the sphere, but you are on ellipses of different, And there are things which can be done there. But we haven't.
Okay.
So I still have a question. When you say that, this here, this is the total spin that follows
exactly.
that?
This is the vector that characterizes your full configuration.
Okay.
And your full configuration wants to go there.
Yeah.
Because I didn't say it, because I didn't have time, but this is the configuration that minimizes the energy of the problem. So this is the absolute minimum of the energy of this problem.
So then you compute how the correlations of those guys going there. This is considered as a domain in your...
In this case, there is no real space.
Yeah, right.
So you have to argue that, going to that direction is like condensing in the zero mode case. But of course, in this case, I don't have a space. Here I do. A similar calculation can be done completely analytically, and there you do have a space, if you work with the large N ON model. So you do the Ginzburg-Landau formulation, but instead of working with a scalar field, you work with an n-dimensional vector field, and you take n to infinity. It's a different n. It's not the n of the number of spins. It's the number of components of your vector. And then the calculations are very similar, but now you have a field that depends on space, and then you have a space dependence on space, and you can identify the zero mode of the wave vectors, and you see that everything goes in the same way. It's very similar. So this is like an ultra mean field for domain growth. The large N ON is a better mean field.
I see.
Yeah.
Okay.
Yes.
Any other question?
I was just wondering if it would make sense to choose not necessarily random Gaussians to the couplings, and I don't know if the spectrum has like infinite support. If it would make sense to.
Yes, we did it with EM time ago. For example, if you look at the matrices that correspond to the dilute graphs, and then you have tails, right? And then the problem is that you have to bound the energy somehow if you use continuous variables, because otherwise the minimum is infinite minus infinity, the energy. So there are a lot of peculiarities associated to this unboundedness of the energy. But yeah, but maybe it's, as I said, I mean, we think that if you have an edge, then all more or less do the same. The details may change, but they will all try to go in the direction of the eigenvector corresponding to this minimum eigenvalue.
But if you don't have an edge, then it would never align.
No, because it has to go,
sure.
exactly. So this makes things a little bit more tricky. Exactly, yeah.
Okay, if there are no more questions, let's thank Letícia again for the...
This is her last question, though, right? So
Sorry?
this is your last question, last lecture for us.
It is.
Yeah,
Yes,
so
yes.
You say so. You're set for that. Thanks a lot, Letícia,
You're
for
welcome.
this
Thank
great
you, Carolina. Thank you.
lectures.
This is one of my favorite